both these projects, the GMT, Giant Magellan Telescope, and ours, the TM, are ready to be advanced to the final design phase. So that's kind of a formal thing within NSF. You're in preliminary design, and we have been. You have a preliminary design review, and we did. And then after some contemplation, the NSF could, if they wish, advance you to the final design phase. So we're hoping they'll do that soon. I would say there's been a lot of activity in Washington that has occupied the NSF people with other matters, in the last few weeks. Nevertheless, I think we're on course to hear from them before too long.
And of all the topics, that TMT is capable of unraveling in the universe,
they wrote up 10 years ago a detailed science plan that said, here are the things we're going to do. And this is taken very seriously by the engineering crew. They said, well, if you want to do this, that, and the other, what does the telescope have to do? And so they wrote specifications for the telescope based on doing the science. Perhaps you're familiar with this concept. But that was 10 years ago, and it's fair enough to ask, how much has science changed in 10 years? Honestly, my special field, the field of dark energy and cosmic expansion, hasn't changed very much. But a field that has totally blossomed, of course, is exoplanets, the discovery of planets around other stars. So we wanted to make sure that even with the new understanding and the broader set of questions and kind of what we do know and don't know, that the telescope is still on the path to being powerful for that work. So we did that. And that was a very healthy exercise. We got over 200 people to help fix this old report. You won't be too surprised to learn that we concluded that the telescope is going to be able to do these new things very, very well. But thinking farther down the line, this telescope is not for 10 years or, it's for 50 years. And so it's a matter of getting the science for today and then the potential for science for tomorrow. Because if you think about it, the technology also is advancing. So it's not just the science, but the technology for detectors and everything is getting better. And we are going to be in a position sooner or later to have a second generation of instruments and to keep on making this telescope right up at the technological frontier. If you think about Palomar, we drove by Oceanside or wherever it was there. And I thought, gee, that's right downhill from Palomar. That telescope was built in 1950. Still, it had led the world for quite a long time because the instruments kept getting better. They went from photographic plates to electronic detectors, all these things that we kind of know about and take for granted. And it isn't at the absolute forefront now, but it's still a very productive scientific place. So I think the lesson from that is that these big telescopes at the frontier of what you can do today are going to last for decades, and it's a generational thing. And I really feel that myself, that I got to use the 200-inch telescope. I didn't build it. I got to use the telescopes at Cerro Tololo in Chile and at Kitt Peak, and I didn't build those. But after a while, you grow into a role where you do help to build the telescopes, and I did help the Magellan telescopes, and I was the head of the optical and infrared at the Center for Astrophysics for a while. So, and I was on actually, I'm kind of proud of this. I was on the committee that wrote the report. This is how we take pride in ourselves. I was on the committee that wrote the report about what we should do after the Hubble Space Telescope, and of course, that eventually became the James Webb Space Telescope.
3D print.
Yeah, very nice work there. It's not that color, actually.
Well, in space, and no one could see where. Right. So wasn't it Hale who went a little bit over the edge psychologically in the building of the 100-inch? Is that
well, it was in between the 100-inch and the 200-inch. So here's the interesting story. If I can remember the guy's name, I will tell you, but I haven't got it quite at the top of my mind. But there was the money for the 200-inch telescope came from the Rockefeller Foundation. And the Rockefeller Foundation did not want to give the money to the Carnegie Institution, which had been running Mount Wilson, where Hale had been working. But Hale had another pocket there where he said, well, I also have this California Institute of Technology I've helped build. And so the money came to Caltech for the 200-inch telescope. And the grants officer at the Rockefeller Foundation was a physicist and participated quite a bit in the design and approval of the project. And when Hale became incapacitated, he was having nightmares. He couldn't do his job. Yeah, I know what you'd call it that. He this guy whose name I gotta remember came from the organization that was doing the funding to be the head of the project. Now, for the TMT, the Gordon and Betty Moore Foundation was a very important part of getting this thing going, and I was the person at the Moore Foundation over the last, since 2015 anyway, not getting it started, but sustaining it for the TMT.
Right.
And I was the observer on the board, but did everything but vote.
Right.
And when it came time to, of course, Ed Stone was the executive, whatever we call ourselves. He's the executive. But when it was time for him to step down, and they looked around, they thought, well, who could do this? They asked me to do it. So I used to be the funder, and now I'm the head of the director of the project, just like the guy for the 200 inch, whose name I should remember.
And hopefully the same fate won't befall you, Bob, because that would be a tragic loss for all of astrophysics. So speaking of your field, so you're one of the few people that can say you proved this guy, this is Albert, good old Albert, wrong. You effectively discovered the accelerating expansion of the universe, courtesy of what we now think might be related to dark energy. But lately, there's been a little bit of a controversy, as our British friends might say, that maybe there is no dark energy. Maybe we live either in a universe where dark energy is evolving or doing something weird, or we live in a void, in which case, you legitimately lost a Nobel Prize. So you don't have to give one back. But would your students, would your former very close colleagues, Adam Rees, who sat there last year, and Brian Schmidt, who I talked to last year as well, tell me, what's the state of play of that field?
Well, I think the first one that you mentioned, that the dark energy might be evolving over time, that has it's very interesting if it's true. And there's a statistical signal that, matches up better with changing dark energy than with constant dark energy. It's data from DESI, this very large spectroscopic survey, and there's going to be a lot more data.
Yeah.
So, when there's a controversial result, you need more data, and sometimes the result gets stronger, and sometimes it goes away. So I think we're at that kind of a point where you should pay attention for sure. And this is really interesting, and we should encourage those DESI people to keep going and do more of their analysis and more of the data taking. So I think that's really interesting and a big possibility. The other one that you mentioned, that maybe we're in a void, and therefore
Timescape for the listeners. I mean, I know it's called Timescape Cosmology. I hope to have the authors of this, controversial but provocative in an interesting way.
Yeah.
So what's your take on this
I'm
Timescape?
less interested in that. I think you have to satisfy many constraints to get a complete picture of the cosmology. So you heard of the microwave background. You got to do that
All right there.
Yeah, got to do that properly. You have to get the ages of things right.
That's right.
And the level of homogeneity that we observe has to somehow be embedded into an analysis of all the stuff. So it is true that if you use this particular model for how things are arranged and how that affects the expansion, that you can get an effect that looks like a cosmic acceleration. But you have to do all those other things too, it seems to me. And the broader picture of lambda cold dark matter kind of picture seems to be a much more comprehensive physical picture. Now, that's not exactly an experimental, test, but I think it does matter that you do not just one thing, even if you do it as well or better, but that you, at the same time, satisfy all these other constraints, the ages of the stars and the clustering of galaxies and all that stuff that we've been working so hard to turn from hand-waving into real statistical understanding.
Right. And a lot of the sort of analysis that goes into the Timescape model, for my listeners who may or may not be familiar with it, has to do with, kind of, I would say, not in a pejorative sense, but manipulation of confidence intervals and, Bayesian reasoning applied to, to this problem to then set a threshold at which you would exclude the proposition that at least, dark energy is a cosmological constant, according to what I've seen. But as you pointed out, it has to, it's very hard to break the standard model, whether it's particle physics or cosmology, right?
Yeah, and I think looking at a particular data set and showing that your model fits it well is not the same thing as getting the whole physical picture, which is not the work of one person or of 10, it's of thousands who have worked so hard on all of this. So I think we should reserve judgment. That to me is less interesting, yeah, just personally, than the DESI result.
Another, maybe more pressing, more important thing, if dark energy goes away, if it evolves, well, it's not a cosmological constant. That's okay. It won't affect us for what 100 billion years. But there's something floating around in space that's gotten in the news recently. It is related to this. This is a piece of Chelyabinsk meteorite, which I've gotten. This is actually a gift for you, Bob.
Oh, because you got that in through the window or something.
That's cool. This was delivered by the United States Postal Service, but this is actually a meteorite. This is from the Campo de Cielo Fall in Argentina. I give these away to those of you on on my email list. One
Or generous fellows.
This is for you. And if you have and that's to go to briankeating.com/YT for YouTube or list. But if you have a .edu email address, like many of our proteges and friends and colleagues do, I'll send you one of these for sure if you live in the United States. So this is a real meteorite. I give it to him. He had to come all the way down and give a colloquium and say, you must have tons of this stuff. Literally. Well, illegal. Yeah, it's illegal to get to export them now. So I got a whole bunch of them. I have here a plate collected by a former denizen of Pasadena. Her name was Margaret Burbage. One of Margaret's old plates, because this is Jeff Burbage's office. I don't know if you knew that. I inherited his office.
He did come here when Jeff and Margaret were here, but that might have been 74 or 5 or 6 or something.
Well, so he passed away about 15 years ago now. It's incredible. Miss him, and Margaret passed away at the beginning of COVID. Not from COVID, but we miss her tremendously too. She was the original founder here. So she actually worked very closely with Vera Rubin, and actually Vera did a sabbatical here. She couldn't get a professorship, as you know, and so, but the Burbage is very kind to her, and she credited them with Margaret, and especially, Jeff wasn't an observer; he was a theorist, right? But with teaching her how to do the spectroscopy, and actually Margaret measured a lot of these rotation curves before Vera did.
Yes, I know that.
She just didn't really.
I know that, and I remembered reading those papers when I was a graduate student, and the penny didn't drop for me either. And I should have thought more about what does it mean about the mass distribution
Exactly.
to have a rotation curve of that shape, and which I was just a kid.
Yeah,
But I should have thought of that.
but you literally have forgotten more than I know. Most people will ever know. But so I talked to Michael Turner not too long ago, friend. He's for what? And I told him, well, we were looking for these axions with the CMB polarization with the Simon's array and Simon's observatory. He's like, and I was like, well, your paper was actually the first one. He's like, no, it wasn't. And, we went back and forth, and I showed him, actually, you have forgotten that you created this term. We popularized in the context of code. Anyway, I'm gonna get back to dark matter.
Yes.
Dark matter is another thing that's quite controversial. You may know in the two different approaches. One is looking at the heavens. One is looking in a laboratory. We have experiments here to look for. What's the current thinking on dark matter? What can TMT do? Perhaps what is the alignment with the future science goals of that amazing instrument?
That's a good question. For the dark matter, of course, something that we could measure is how clumpy it is. And we could do that because the telescope will have fantastically good angular resolution. So if you're looking at a bunch of stars, say a globular cluster where there are lots and lots of stars in the field very close to one another, and you measure their positions over time, you could see the effect of a medium-sized black hole or clumpy dark matter on the positions of the objects. So we're not going to image the dark matter, but we're going to see the effects of it. And of course, that's the whole story here. For the physicists, trying to see the dark matter bump into a xenon nucleus or something like
Right
that.
here, yeah.
That's a great idea. And we thought for a long time, I mean decades now, that it was just around the corner and it was going to happen. And now, tremendous ingenuity has been devoted to this, and a lot of xenon, by the way, which is quite bad. Yes, it is quite, but you can use it for something else after you're done. There's still no evidence for the weakly interacting massive particles, the WIMPs, that uh, Michael Turner also was very influential in popularizing.
You touched upon the DESI results recently,
Yeah.
which were phenomenal. They've been out for about a year. I'm devoting a special explanation episode of the podcast in a couple of weeks. I don't know if it'll be out by the time this comes out, but one of the interesting conclusions has come from a colleague here, Professor Dan Green, who claims that there's evidence for negative neutrino mass. So one of the main outcomes of DESI has to do with neutrino mass, as well as many other science goals. So you're shaking your head, maybe.
Well, not because I really know
No.
or have a strong understanding, but it's very novel, um, and it's could be so, I guess, but it's not an area where I have any expert.
No, but your book was very formative in my career early on as a graduate student, The Extravagant Universe.
Yeah.
Wouldn't this be sort of the most extravagant thing that you could think about? Negative mass, or even, well, first address that. So, how extravagant has the universe gotten more or less extravagant in the 20 plus years, 26?
Well, it is surprising to me, not that we've made so little progress, because there has been progress, and the signals have gotten stronger, the measurements are way, way better. Instead of having 10 supernovae, we've got 1,000 in these samples, and we're soon going to have tens of thousands and many more. So the evidence is really better. But what's been surprising to me, and what you're hinting at, is that there's a conceptual gap. Where is the new idea that is so persuasive that everybody says, well, that must be the right story? And you can think of other areas like the one you work in, where the idea of inflation somehow seemed like just the right thing. That is still what everybody talks about. And if you can make a measurement, which I know you want to, that shows that that's really the case, that'll be a big step forward. So going from an idea that kind of sweeps the field, but, still leaves room for speculation, to a story where the evidence is so strong that it really tells you what the story is. That takes a lot of effort. And so just having a good idea is one thing. Having a good idea that other theorists think is interesting, that's better. Uh, but even that doesn't prove it. The thing that is, and even when you have a prediction that's matched by the data, that doesn't exactly prove it, but it sure makes you think you're on the right track. And, the last 100 years or so have been a fantastic story of coming to some deep understanding of what the universe is. It's not exactly where it came from and so on, but, people care about that too. And there are different models for how things could have begun. The inflation model is the one a lot of people like to talk about, but, there are others. So I think, you have to have a strong enough motive to carry out the observations, but you also have to keep an open mind about what it might mean.
That's right. And in that vein, as we wrap up, want to be a good, co-host here and not make you miss your coffee and cookies that you're legally entitled to.
Yes.
Is another concomitant measurement that we'll get with the CMB, hopefully, and DESI might get as well, sorry, and that's of neutrino mass themselves, negative or positive. But that as a study, I want to ask you not in terms of technique or technology, but that would be the first time, as far as I can be aware of, that an elementary particle's mass would have been measured by an astronomical, not a laboratory-based experiment. And knowing the sociology of the field so well as you do, from your just illustrious career, what do you think would be the reaction? I mean, I've asked this of particle physicists too, but do you think it would be accepted? I mean, do you think that those stodgy, people working in deep underground labs at the LHC or whatever, do you think they're really going to, really my former, co-author on audiobook, or she at least read the intro of Galileo's dialogue, Fabiola Ligionati. Is she gonna is she going to accept the measurement of the from these astronomers looking around with a telescope?
Well, I don't know. You can't tell other people what to think.
That's true.
But my guess is that the cultures are sufficiently different and the ways of going about things are sufficiently different that it would take quite a long time
Yeah.
for that to happen. But look at the solar neutrinos, for goodness sakes. There, we don't exactly know the mass, but we know the difference
That's right.
of the mass. Well, that's a real step forward, and that everybody accepts
Yeah.
that now from the neutrino mixing. So I would say these things that are at the boundary of the various tribes are the things where we have to be really cautious and helpful to each other.
Hmm.
The physicists tend to think they know better,
Yep.
but sometimes the results come from a more straightforward way of doing things that astronomy is used to.
Yeah, and as you say that, just thinking about the greatest breakthroughs did come about because of the comity of man and woman and the agreement between formerly disparate fields, everything from climate change to, as you say, neutrino mass differences,
Yeah.
and even things like speed of light, relativity, historically. So
Yeah, right.
so very
So
good.
that's a good lesson,
Yeah,
and that's why people should listen to your podcasts.
and go to other people's talks. Don't just say it's I, but yeah, go. You better go. That's ultimate in being Bob Kirshner. It's always a pleasure to be with you. We should do this more often.
Thank you, Brian. Every time I come down Interstate 5, I'll stop in here.
Thank you. You heard it here, folks. Thanks very much. Stay tuned for another episode of the Into the Impossible podcast with yours truly. Thanks a lot, Bob.